So welcome back to Math 210. So we're starting out in section 4.7. I want to do this problem, this is number 34, that I always struggled with when I was an undergraduate student, and you know, now that I'm teaching, I like to use it to illustrate like an example of what's going on. Sometimes students say, you know, like you give us the easy problems in class and then like the hard problems for homework. So what's up with that? So I'll try doing a problem that's a little bit more substantive right now. But before that, are there any questions from anyone about anything related to the course? Okay, as usual, be welcome to drop them in the chat to everyone or to me personally, no big deal, and I'll be looking out for those. So here's the idea. The idea behind this optimization problem is, you see it framed different ways. It's not like a super great picture. Let me try again. One way you see it framed is you've got a rain gutter, and you can like choose this angle theta. So you can imagine like if theta were, so this is like a, you know, think of this as like the x-axis, and usually you measure your angles counterclockwise. So like if theta were equal to 0, both these sides would be closed and you'd have a straight line. If theta were equal to 180, then they'd both be sort of flush, and you'd have something, you'd have also a straight line that's just kind of longer. So when you've got like theta equals 0 or theta equals 180 degrees or pi, like in either of those situations, this sort of collapses onto itself and it has 0 area. And the problem is basically saying, can you find the angle theta that maximizes the area of the trapezoid? And the information that we're given is that the base is length 2, and these two sides together have length 2. So I know you were to self-study this, but just to give a brief overview, when you're doing an optimization, you're usually trying to find like the maximum or the minimum of something. In this case, we're trying to maximize the area. And ultimately, you need to construct a function that depends only upon theta, and then find like the maximum and minimum value of theta. So you need to find a function, a of theta, and importantly, you need to find an interval to maximize or minimize over. Because if you think that like theta goes from like negative infinity to infinity, it's easy to find functions that go from negative infinity to infinity that have no maximum or no minimum. This theory that we've done before break, this like extreme value theorem stuff, this like finding the extreme values, it's all predicated on the idea that you've got a function on an interval. So you need to find a closed interval upon which your function is defined. So you're kind of wanting to find a closed interval for the domain. And so the way this problem was stated is it just said, look, here's the setup. You can let theta vary, and please find the value of theta that maximizes the area. So part of the problem is going to be finding a function for the area that depends only on theta, but don't neglect this second point too, which is to define the domain of the function a of theta that makes sense. And I've given you a clue here because physically it doesn't make sense to have an angle that's less than 0. And when your angle is 0, this picture collapses in on itself and the area is equal to 0. That's not a maximum, that's a minimum. So like a of 0 equals 0. And physically you can imagine that as you're increasing theta, the area gets bigger and bigger and bigger for a while. And then as you keep on getting closer and closer to 180 degrees, you're all of a sudden then collapsing in and becoming 0 again. So in this case, I expect my domain to be the closed interval from 0 to pi. And then I remember this extreme value theorem, which says if you want to take a function like area of the trapezoid, depending on theta, then the maximum and minimum values either occur at endpoints or at a critical point. And in fact, I've got a setup here where it's clear that the minimum values, area can't be negative. So if you've got a place where the area is 0, that's a minimum value. So it's clear that the minimum values are attained at the endpoints, and therefore the maximum must occur at a critical point somewhere between 0 and pi. So just from having the perspective of understanding our setup, we already know that the maximum should occur at some angle between 0 and 180 degrees. That's all completely reasonable. And the mathematics that we've done so far in this class verifies it for us. So now the two steps for solving the problem, or maybe like I'll put down like a third step, which is like maximize or minimize, or optimize. Like in this case, it's maximize. So maximize this function a of theta on the given interval. And so that's the general procedure. And now that I've said the general procedure, I will modify it a little bit to do this problem, because if you stick with theta as your variable, it does make it a little bit more difficult. That's the reason why I struggled with this when I first saw it in calculus, like, I don't know, 24 years ago or something. That tells you how infrequently people update these problems. So you want to first ask yourself, like what's the area of a trapezoid? So here's a little class participation. Do you remember, or can you look up any formula for area of a trapezoid and maybe put that in chat for me? So get your Googling skills ready. I'll give you another minute. Please look up or try to remember what's a formula for area of trapezoid. And anyone you can remember or look up, put it in chat. Great, seeing some answers, thank you. Yeah, the area of the trapezoid. And so you're all remembering, I'm sure, like if you have area of a square, it's base times height. Area of trapezoid's a little bit different. It's the average of these two lengths times the height. So height, of course, is this straight up and down length, so h. And if this number is a and that, maybe 4 is equal to b, then the area is a plus b over 2 times the height. Which makes a lot of sense. The way you can prove that, by the way, is if you cut out this triangle and paste it back here, you'll actually end up with a rectangle that does have base a plus b over 2 and height h. How does this, we have to take this and convert it into a function, based on this angle. And here's the problem, which is that, like, if you try to use angle theta, you're not going to have a very good time to be able to figure out, like, what is h. I think I can figure out h using trigonometry, but it's a little bit more difficult, because what I'm really interested in is this right triangle, and I'm really interested in this angle, and I'll call that angle maybe psi. And what's the relationship between theta and psi? I'll let you think about that for a couple seconds. So, like, what do theta and psi, like, how do they relate to each other? So since this is a right angle, and theta is the angle from the horizontal to the, to the line, what I'm thinking is that theta is equal to psi plus pi over 2. And so here's the trick that really kind of makes this problem work. Like, if you want to write a formula for the area in terms of an angle, it's more convenient to do it in terms of psi instead of, like, theta. So actually what I would ask you to do is really, like, find the area function, like a of psi, and optimize that. And then when you're done and you've found psi, whatever your answer is, just add pi over 2 to it. And that'll be your answer for theta. That's sort of my idea behind that, because you're allowed to change your variable. Like, just because theta was presented to you, and just because you have to write your answer in terms of theta, doesn't mean that you can't change the variable if it allows for your, the computations or whatever to go a little bit easier. And in this case, it's going to be easier for me to figure out h in terms of psi than it is for theta. So any questions on that? And so let's actually try to figure this stuff out. So let's introduce some more terminology. So I do need to understand this, top length a little better, and I'm going to break it up into 3 pieces. So I know this middle length is equal to 4, and let me just call this other length x. And since, these angles are the same, by symmetry, this other length is also going to be equal to x, right? And so this other angle, of course, also equal to psi. So breaking up the rectangle in that way. And a plus b over 2 now becomes 4 plus 2x plus 4 over 2, which is equal to what? 4 plus x? Isn't that right? So the area is base times height, so height times a plus b over 2, which is now height times 4 plus x. So I've got h times 4 plus x as my area, but I'd like to write this completely in terms of psi. So I need to write x and h in terms of psi. So what relates those together? Probably trigonometry, right? So like what do I have going for me? If I look at sine, let's just start writing down some of these functions. So like sine of this angle is what? Opposite over hypotenuse? X over 2. And what about, I guess cosine would be the other one. Cosine of psi would be adjacent over hypotenuse. H over 2. So that's telling me that x is equal to 2 times sine of psi, and that h is equal to 2 times cosine of psi. So if I want a formula for area in terms of that single angle, it appears to me that I'll be able to write a of psi is equal to h, which is 2 cosine times psi times 4 plus x, which is 2 sine of psi. And you can, I don't know, you can multiply this out if you like. So this is what 2 times 4 is 8 cosine psi plus 2 times 2 is 4 cosine psi times sine psi. And I don't want to get too into like trig formulas or whatever, but if you remember that 2 times cosine psi times sine psi, that's a double angle formula. So you can rewrite this if you want as 8 cosine psi plus 2 sine of 2 psi. I don't know if that's going to be helpful or not. I may be shooting myself in the foot for like doing the calculus later. We'll see. But I'm using the double angle formula there. 2 cosine psi sine psi equals sine of 2 psi. So now I've got my function that returns for me the area of the trapezoid just based on that angle, which is actually pretty cool. Even just that in itself is pretty neat. I want to maximize this on the interval from theta goes to 0 to theta goes to pi. And therefore, the interval on psi that I want to maximize, psi is theta minus pi over 2. So psi is going to go between negative pi over 2 and pi over 2. When psi goes from negative pi over 2 to pi over 2, theta will go from 0 to pi. And you should be able to verify that at these two endpoints you do get 0. Otherwise, our formula is wrong, right? And like if we plug in pi over 2 or negative pi over 2, that's the place where cosine is equal to 0, and that's the place where sine of 2 times pi over 2 sine pi is equal to 0. So that's nice. That's a nice reality check that it's like looking good. And so now you just want to go off to the races and maximize this. Maybe I should even stop here because this is the part that you're more familiar with. The part where you're more likely to need my help is maybe like setting up that function to begin with. But I don't know. I'm kind of curious. So let's try. Let's take the derivative and let's use this formulation. So the derivative of cosine is sine. The derivative of sine is cosine. And then the chain rule tells us to multiply by 2. calculus form. And you're setting this equal to 0 to try to find critical points because the max can only occur at a critical point. And yeah, you're just going to get 4 cosine of 2 psi is equal to 8 sine of psi, and dividing both sides by 4. Cosine 2 psi equals 2 sine of psi. Yeah, I don't know, is there an easy way to see that? I mean, you could figure that out graphically, but I think maybe the double angle formula. So I was saying before, the double angle formula might have tripped me up a little bit. Let's try this without the double angle formula and see if it gets simpler. Let's take derivative like over here, so giving me -8 sine psi plus, this will be product rule, so this is 4 times derivative cosine, which is negative sine, so that's -4 sine squared psi, and then plus 4 cosine squared psi. And if you set this equal to 0, it doesn't appear to help, right? That doesn't seem to make it any better. I don't know. Let's convert, maybe there's a trig identity I'm missing. So let's convert cosine squared psi into 1 minus sine squared. So if we set this equal to 0, we've got -8 sine psi minus 4 sine squared minus 4 sine squared minus 8 sine squared psi, and then plus 4. Did I do that algebra right? Correct me if you want me to re-explain something, or if you want me to, or if you see a mistake. And so I'm setting this equal to 0, and let me multiply both sides. So setting it equal to 0, I can multiply both sides by -1 to arrive and rearrange the terms to arrive at 8 sine squared psi plus 8 sine psi minus 4 equals 0. I could divide both sides by 8 to give me sine squared psi plus sine squared psi minus 4 over 8, so minus 1/2 is equal to 0. And this is now, so what can I erase? I still want to know that theta was psi plus pi over 2. And this is now like, it's a quadratic, it's a polynomial in sine of psi. So if you write y equal, in other words, if you write y equals sine of psi, you'll get y squared plus y minus 1/2 is equal to 0. And so you can ask yourself if you can factor that. Can you factor that? Can you find two numbers that multiply to -1/2 and add up to 1? I don't know. Well, we'll try the quadratic formula. We'll try quadratic formula. So y equals -b, so -1, plus or minus the square root of the discriminant square root of b squared, minus 4 times a times c, so 4 times 1 times -1/2, all divided by 2 times a. So here's the two roots. So that's going to be y equals -1/2 plus or minus, what is it? 1. So 2 minuses is plus. 4 divided by 2 is 2. So 1 plus 2 is 3. So, I mean, you could have guessed that like root 3 is going to show up there. So the two values of y are going to be -1/2, or I'll rewrite this as root 3 minus 1 over 2, and y is equal to negative root 3 minus 1 over 2. And since y is sine psi, you'll get sine of psi is equal to, root 3 minus 1 over 2. And sine of psi is equal to root 3 minus 1 over 2. And I guess the question is then, can you find an angle that gives you that answer? That doesn't look very standard to me. So like, unless I messed something up, I think that doesn't look very standard to me. So you'd have to just kind of approximate that. So what I would do is I'd even go into Desmos. So like, yeah, I can see why there's like maybe some student frustration for problems like that, because they do require like a lot of these like small extra steps when the numbers don't work out like super well. But let's try to push it through, and let's see if we can get, like I do like everything honestly in the recording, let's see if we can get an answer and see if it makes physical sense. So we're looking at y equals sine of phi, but I'm just call it x to make Desmos happy. And this is supposed to be equal to square roots of 3 minus 1 quantity divided by 2, and there's another root there. And remember, we're restricting the domain from -π/2 to π/2. Yeah, so it looks like there's an intersection there. And what was the other one? Y equals, there should only be one solution. So y equals negative square root 3 minus 1 over 2. Yeah, good deal. So in our range, so if you don't specify the domain, then you'll end up in a situation where you have like two competing solutions with each other, and that's not very good because that doesn't make physical sense. But since we specified -π/2 to π/2 at the beginning, our graphical exploration is showing us that like we can discount this other solution. And by the way, like realizing that, um, you know, sine squared phi plus sine phi minus 1/2 was quadratic in sine phi. That's a strategy in and of itself. So that's something that now that you've seen it, I hope you can employ that. So it looks like the angle theta we're going to get is like roughly 0.375 radians. So that's kind of my, like that's what I can do for you. So that looks like, yeah, is that a well-known angle? I don't know, but my answer is 0.375 for psi. And let's graph the function. That original area function, I guess I erased it, but kind of so invested in this. Like I want to graph the function and see if that's actually a maximum. So if you want to help me out and just write down my original area function and put it in chat. Otherwise, I'll just figure it out again. It was like a of psi was like h times 4 plus x, which was something like 2 cosine psi times 4 plus 2 sine psi. Hopefully I didn't make any mistakes, but if I, let's plot the graph of that on Desmos and see what's happening. So let's take y equal to, so let's hide the graph of sine x. So we'll locate the point 0.3750. Let's zoom in a little bit, because this was our candidate for the location of the maximum. So we'll keep track of that and hide everything else. And now let's graph. Now let's graph 2 times cosine x multiplied by 4 plus 2 sine x. 2 cosine x multiplied by 4 plus 2 sine x. So this is my function that was going to give me the area of the trapezoid. And let's restrict its domain from negative pi over 2 to x to pi over 2. I'm hopeful. Hopefully I'm not embarrassing myself. Oh, cool, it's working out. I was so afraid I was going to like make some stupid mistake and then it would just be completely wrong and I'd be like, yay, I'm a professor of math, cool. No, but it actually worked out. It's so, I don't know how you feel about this because, you know, like in the online world, I can't get much feedback from you, but I think it's just great. So this is, to put it in perspective, so this is the graph of the area function depending on psi. You can see it does have a maximum here. We've identified that maximum like with calculus. It didn't work out like in a very easy way, but it did work out in a way that we could estimate. So 0.375 radians. Oh, I didn't share this with you. You folks gotta yell out if I'm not sharing it with you. Sharing is caring. I've got to apply my skills learned from kindergarten and share. This is okay, so this is what I've been doing. So I plotted the point, 0.375, and then I plotted the area function to just see whether it had a maximum there, and it does. And so that's what made me happy. So there you go. And if you return to the problem, we're supposed to find the value of theta, and remember that theta was equal to psi plus pi over 2. And our approximate value for psi that we got from applying the quadratic formula and then just using Desmos to approximate the value of psi, given that the sine of psi was equal to this number, we got that it was approximately 0.375 radians plus pi over 2. So this is my final answer. That's the answer that does it. And if you want to convert that back to degrees, you can, and then you'll get an answer that's approximately in degrees. I haven't looked at that problem in probably 10 years until just now, and I can see why it stressed me out when I was an undergrad, because back when I was a graduate, we didn't have figured out the value of psi like in my head by just comparing it, unless I'm missing something. So I don't feel quite as bad for struggling with that now. Doesn't that make you feel great that I don't feel as bad? Who cares about my calculus class 1,000 years ago? Okay, are there any questions or comments on any of that? So I know that was a long amount of time to spend on one problem, but there are simply lots of issues that go into optimization, and each problem is different. There's a general strategy, which is find your optimization function. You write that function in terms of the variable that you want to optimize. Determine the domain, the closed interval upon which that optimization function is defined. Then you find the extreme values by setting the derivative equal to 0 and solving that equation. You may be able to solve that equation simply, or in this case, I was not able to solve it simply. I had to make the substitution y equals sine of psi, use the quadratic formula, and then use a computer algebra system to estimate the value of psi by looking at the intersection of sine of psi with my with the answer that I got from the quadratic formula. So doing this problem required not just understanding the individual steps, but also required the ability to put those steps together in sequence. And that is sort of like a capstone achievement of the first, 2/3 of the class. And it is something that takes time and effort. It's true. But it is worth it. So this is our most complex learning objective so far. And that's why I went back and tried to do one of these problems, even after having you self-study it on Wednesday. So final chance to ask any questions or comments. So what I'll do now is briefly introduce the next topic. And you may have already watched my videos on this. If you haven't, check that out. I typically post the relevant videos the day before, but the whole 85 video series is also linked on the Google Classroom, and you can just check that out and pick and choose whatever you want to watch. So what we're going to go into is this concept of integration, and the earliest application or motivation of this did come from physics. It came from the idea of trying to find out like what is the area like above the x-axis and under a curve. And to help motivate this, if you go back to high school physics, if you you might remember that you have this formula which says like distance is equal to velocity times time. And this formula is true like under a certain assumption. It's not universally true. It's under a certain assumption, which is to say that if your velocity v is constant, then it's true that the distance you traveled will be equal to your constant velocity times the length of time that you traveled. And if you want to illustrate this law graphically, it's saying that you're traveling some time interval, and maybe this should really even be like delta t. Because your time interval maybe goes from t1 to t2, and then delta t is t2 minus t1. It's the length of that interval, right? And then you're traveling at some constant velocity. So x-axis is time and y-axis is velocity. That velocity is constant. And then the formula for the distance that you traveled is just velocity times time, which is just base times height, right? So the formula for the distance that you traveled is really just the area of that rectangle. And what if you were, traveling at some speed, and then all of a sudden you jumped up and started traveling at another speed, and then maybe you slowed down instantaneously and traveled at another constant speed? Then if you were to look at the total distance that you traveled from T1 to T2, you don't have a universal formula you can apply to that, but you can apply this formula to each period of time upon which you are traveling at a constant velocity. So in other words, you can use distance times time here to get this area, this distance times time there to get that area, that distance traveled, and similarly here. So the total distance you traveled would therefore be the sum of the three rectangles. But there's a very natural question that people asked, way back then. We're still in the 1700s here. Excuse me, why am I coughing? I got something in my throat. So we're still in the 1700s here, asking ourselves as mathematicians and physicists, like, what if you're traveling at a non-constant velocity, which is mostly what happens. Whether you're looking at like something moving under the influence of gravity, or like a particle, or just any of us driving to the store in our cars with the velocity speeding up and slowing down. So like, what if your velocity curve looks something like this? Maybe look non-constant. Then if you want to calculate the distance that you've traveled, more generally, it would be displacement, because your velocity could be positive or negative and travel forward and travel backwards. But the way I've drawn it, the velocity is positive, and you're looking at distance. So the distance would still be the area under the curve, wouldn't it? So that makes total sense. Or if it doesn't make total sense, then consider this explanation that the physicists kind of did. They said, look, like, as long as your velocity is continuous, then maybe you can like for this small little section, when your speed isn't changing too much, you can approximate your velocity by this constant. Like you can approximate your velocity in this section by this constant, even though it's not quite accurate. You're, you know, in other words, you take an approximation of your continuously varying function and approximate it by these sections. And you're not going to be completely right, but you approximate it by these sections where you're moving at a constant rate. And if you use distance times time on each area, then you'll get an approximation of the total distance that you traveled. And you can see as you make the approximations better and better and better, you'll get closer and closer to the area under the curve, which gives us this idea that the actual distance you traveled for non-constant velocity should just be the area under the curve of that velocity. And when you're taking an approximation that gets better and better, when you're increasing the number of rectangles that you're using and adding them up, it looks like we're taking a limit, doesn't it? So in fact, the way we're going to figure out like the area below the curve above the x-axis is to actually approximate with these rectangles and then take a limit as the number of rectangles that we use to approximate increases without bound. In other words, take a limit as the number of rectangles approaches infinity. And so something like that seems like it might be very hard to calculate, but the great achievement of calculus is that there's a formula called the fundamental theorem of calculus that basically lets us calculate things like this using our knowledge of derivatives. So that's what's coming ahead over the next few weeks. And we'll do it all in detail and give you some good time to practice. But that's where we're headed. So we'll fully engage next time with using these summation notation, using approximating areas by using rectangles, talking about the different ways that we can approximate. So if you want to get ahead of that, look at section 5.1, look at section 5.2, and go watch some of those videos. So thank you everybody for your time and attention, and we'll see you next time.
Thank you.